Welcome to this video on solving the Ramsey model. The Ramsey model is one of the big canonical models in macroeconomics and therefore an important model to know how to solve. If you can solve this, then you can solve a lot of other models, as I will also talk about here. So I'm importing some standard stuff, and then I'm importing from the Ramsey model, I'm importing Ramsey model class, which is the class that we will be using in this notebook to solve the model. I will get back to that. But let's just talk about first what the model actually is. So the model is set up in discrete time, and time is indexed by t, and it's 0, 1, and so forth. Demographics are simple. There is only a single infinitely lived households. Households supply labor exogenously. We said this capital N equal 1, and earns a wage W. The return on savings is RT plus 1. And utility can therefore be written as the total utility is the discounted future utility, where the utility function is the CRA, a utility function standard. And you can write the budget constraint of the households as cash on hand is equal to what you get in return on your previous end of period asset holdings. What do you get in labor income? And then given what you have on cash on hand, if you consume something, then you have less end of period assets at the end. So the households are sort of simple in this way. Firms, they rent capital at a rental rate RK, and they hire laborers at the wage rate W. Firms, they have access to a production function where they produce goods based on the input of capital and labor, and specifically we will be using a CES production function as this one. Profits are therefore what we produce minus labor bill minus the rental bill for capital. So the equilibrium in this model can sort of be written in terms of 6 conditions. Households must maximize utility. Firms must maximize profits. Then we have that the labor market must clear, so what the firms demand in labor must equal what the households supply. The goods market must clear, what the firms produces must equal the sum of consumption and investment. The asset market must clear, so total savings of the households must be equal to total capital. And here we have that the rate that the households earn as an interest rate on their savings, that's the rental rate on capital minus the depreciation rate of capital. And finally, capital will follow a law of motion where capital today is capital tomorrow with some discounting plus investment. I will not go through the mathematical analysis of this model, but if you do, then you can sort of derive first order condition for profit maximization, with saying that the rental rate should be equal to the marginal product of capital and the wage rate should be equal to the marginal product for labor. So there's an E here, which should be an L. Great. And this looks like this in this case. You can also, from the utility maximization, you can derive a standard Euler equation where the marginal utility today should equal marginal utility tomorrow, discounting with the how you discount future utility, and then also taking account of that if you save some money, then you get a return on it. You can write it in this direct way, and we can sort of substitute in the expression for what the interest rate actually can be written as in this way. We can also rewrite the capital accumulation equation as I stated before, where instead of investment I write output minus consumption, because if the goods market clears, that must hold, and I can write production as the production function where I substitute in that we know that because labor is exogenous, it will always be equal to 1. Okay, so this is just the model. If we now want to think about how we will be solving this model, then we can show that we can sort of summarize all of the model in a nonlinear equation system, as written as this. So here the boldface H, that's sort of stating the whole equation system. Boldface K and C, that is sort of the vector of capital now and into the infinite future, and consumption now and into the infinite future. And then this big equation system is a series of equation system, one for each point in time, where H0, that's the condition that must be fulfilled at time 0, and the condition that we can sort of show that this model boils down to is the Euler equation I stated before, and the capital accumulation equation I stated before. To know that these equations are only functions of c and k, and that's why I did sort of the rewriting of them just above. So these are sort of written, instead of having an equal sign here, it's a minus sign, so we have that they should be equal to 0 on the right hand side here. You can sort of verify that if these two conditions are fulfilled in all periods, then all the equilibrium conditions are fulfilled. We will talk about these paths of k and c as the transition paths. So how does you transition to the steady state? If you find a solution to the equation system where k and c are constant, then that's called a steady state. To solve this equation system in practice, we will sort of do it in two steps. Or in the sense that we will first assume that all variables are in steady state after some truncation horizon. And by this I mean that at some period, let's say 200 periods, 500 periods into the future, then we will be back at steady state no matter where we start. And in that sense, we can sort of think about this as only being 200 or 500 periods long vectors instead of infinitely long vectors, which we cannot handle on a computer. Then, once we have assumed that, then we will be calculating a Jacobian of this big equation system with respect to both k and c around the steady state. And then we will simply solve the equation system using a Bruyton solver that I have written. We could also just put this into SciPy optimized root, and we will solve it in this way. So remember that sort of finding this Jacobian, that would be very time consuming to do by hand, but it's rather easy to do numerically. The Jacobian is just a gradient, i.e. the matrix of the applied errors in the equation system when a single k or single c changes. So that's what we will be liking to do. Okay, let me first show you sort of how working with the model looks like. So when I initialize a model, then this will be a model where there will be some parameters, there will be a steady state, and there will be a path or transition path of these variables. So let's do that. So this you can see that sort of when it's initializing the model, it's calling setup and allocate. We will look at what those functions do in a minute. Then we would like to find a steady state, and we will target a capital output ratio of 4. We will force steady state output to be equal to 1, and then we will adjust beta and gamma. So that's the technology level in the production function to achieve that these things are fulfilled. We can do that here. Then the code has various things we can do with it. Here I set the initial lagged capital equal to the steady state capital. I set technology, consumption, and capital equal to the steady state values. And then I evaluate what is the errors along the path. So what is the errors in this equation system up here. And because I'm starting in the steady state and all things are at the steady state, then they should logically get out zeros. So I'm seeing here that all the errors should be close to 0, and I survive this. Therefore, I know that my code is good, and I will be calculating my Jacobian. That takes half a second, so that's rather fast. And then I can now set something that's another initial value for lagged capital. Here I set it equal to half of steady state capital, and then I can solve the model, find the transition path, and I can plot what's going on here. So I'm plotting the lagged value of k over time, and you can sort of see that I'm solving this model over 500 periods, and it goes rather quickly back to the steady state value of 4. So the code seems to work. So now we need to understand what the code is actually doing. So what we start with to begin with is this Ramsey model class. Let's go into that. So this is the file with the Ramsey model class in it. We have the initialization, we have a setup, we have an allocate. We know that we have called those when we initialize the function, initialize the model. Then we have a function for finding steady state. We have a function for evaluating errors on the transition path. We have a function for calculating the Jacobian. We have a model for solving. And we have sort of two extra functions outside the class. One is the production function So that's simply implementing, once we know our gamma and our k lag, then we can just evaluate what will production be and what will the rental rate and the wage be according to the first order conditions of the household, of the firm. And then we have a Brighton solver, which I will not go into here, but it's simply a solver which, based on an initial guess in a Jacobian, solve the equation system. You can look into that yourself if you are more interested in how that works. But in initialize, we simply create the SS and the path as simple namespace. Then we call setup and allocate. And in setup, we set some parameters for the households, for the firms, the initial value of capital, and some sort of technical stuff about which solver we will be using when we're solving the model, and how long the path will be, what the truncation height horizon will be in this model. So let's close this, and in allocate, I'm simply going through all my variable names, and then I'm allocating something that's equal to the path here. So that's simply taking care of that. Close this. Then to find the steady state, I can sort of, what I am doing in practice here is I'm saying I want my steady state to be this number I put in here for capital. Then I find out what my production function is if I set in a gamma of 1. Then I come out with a y, and then I say my gamma should equal to the inverse of this, because then my y will be equal to 1. I sort of put it back in here, the values, and then I check that actually my y is equal to 1. Then I can calculate, based on this calculation, what the rental rate and the wage rate must be, because that comes from the first order conditions of the firm. Then I can calculate what the interest rate will be, and to have sort of that I can have a steady state, then the Euler equation requires that the discount factor is equal to 1 over 1 plus the interest rate. And then I can also see that consumption steady state, that must simply be what is production minus what is the amount of investment that's required to keep capital constant. And then I print out those values here. Okay. Now begins sort of the more technical part of this. So if we want to evaluate the path errors, so remember what were those? So those were the errors that when we set up the equation system, then there were sort of 2 errors for each time step, and we want sort of to be able to evaluate this equation system and return those errors. So let's see, how do we do that? So here we pull out what is the path of C equal to, and we find out what is C plus 1. So here I take my path from not the first one, but from the second one onwards, and then I add a C at the end. For K, I can take the K out, and I want to have my K lag to be equal to exactly my K path, not including the last one, but then adding this initial value at the beginning. Then I simply evaluate what my production and what my prices should be. I evaluate then what the interest rate should be, and I append again the steady state interest rate at the end of this. And then my errors, they are 2 times how long the path is. And for the first set of errors, it's the Euler equation errors written just as in the formula. And for the second errors, it's the errors in the capital accumulation equations. And finally, I just ravel these to get out a vector, because in the end, the solver doesn't care about this being 2 different things. It's just caring about that there is these errors as a vector in total. Okay, so this is the way I can now evaluate the errors. Remember that when we did this with the steady state input, then we got that they were all 0. Now we can also calculate a Jacobian to this problem. And the way we do that is that we set up the Jacobian. The Jacobian is that there is 2 times capital T path in inputs. So it's a big matrix, right? Remember, this is 500, so this is 1,000 times 1,000. It's a big Jacobian. we start by saying, let's create an X, sort of the input to this, which has the C and the K into it, and we take this as a vector. Then we set our C and K equal to the values of C and K in steady state, and we evaluate what is our base errors. These should in principle be 0, but they're just very, very, very small numbers, so we have sort of a baseline here. Then we loop through each possible variable that we could vary, so that's these 2 times capital T path, and each time we copy our X in steady state, and to the I in index here we add a small number h, which I'm setting here to 10 to the power of minus 6. Then I do this in vector form. I reformat it into a 2 times t path array, and I put in the first row of it into C and the second row of it into K. I evaluate the errors. These are my new errors, and then I calculate a numerical derivative in terms of how does the errors look like relative to the base errors divided by the time step. And this is just a long loop doing this many times, and then it's calculating the big Jacobian in this way. And then if I want to solve my model, then I write up a function as for the equation system, which take in an x, which is again just a vector. I reshape it into a 2 times t array, put the first one into C, the second one into K, and then I evaluate the errors and return those. I guess on the steady state as an initial guess, and then if I'm using Brighton as is my baseline setup, then I call this Brighton solver and do it with the Jacobian. I can also just do it with optimized root, where I use this method for doing it, for solving it. You have to work a bit with what the factor here should be to get it to work. If it's too high, then it takes 2 large steps, and then it's not working. After I'm solved, I just evaluate the equation system of finite time to ensure that things are working. Okay, so that's actually all of the code for solving this model. And you have already seen how it can sort of be done in practice. You set some initial value, and then you solve, and then you can see what the result is. This is a good time to pause the video and sort of go through the code and think about, do you understand everything, or what do you need to run yourself and sort of check what's going on. Otherwise, let's show you some other stuff that we can do with it. First, let's just check that actually if we use SciPy instead, use the SciPy solver instead, and do all the same steps, then we get the same results. We will see they lay like exactly on top of each other, so things are good here. Another thing we can now do is we can make shocks in this model. So we can now set that we actually start from the steady state in terms of capital, but that the gamma, the technology, has some other path. Here I'm saying that it's has their steady state value, but then it's deviating by 10% from steady state. It added 10% to steady state, and then this is a number which to begin with is 1, but then it's 0.95 raised to 1, 2, and so on, and therefore it sort of goes back to steady state. This is also called an MIT shock. So it's a household where it's a shock where the households do not expect there can be shock. They know the full path of the shock when it arrives, and they continue to believe that there will be no further shocks in the future. So it's a perfect foresight model, and a shock is therefore called an MIT shock. But we can set this up, and then we can solve the model based on this. And you will see that's solved rather quickly. You might wonder, how does Sol know that something has changed? And that's because we have changed this up here. And when that changed, then if we go into solve, we can actually not see it anywhere here. But if we go into, we know that it calculates the errors here. And if we go into the errors, then we can see that in the input here, it will change the y, r, k, and w, and therefore changes in the other variables are required to ensure that these errors continue to be 0. And therefore it takes a few steps for the solver to do it. To begin with, the error is large, but then it gets smaller and smaller and gets small enough at some point. And therefore you could see that this actually seems to work. we get a persistent shock to technology, and we have that capital, because now it's more productive to produce stuff, we accumulate more, and we sort of therefore also produce more. So now we could of course begin to change this shock. So we could say that, what if this was 98? We succeeded, and now we say, okay, this took longer. Now you might wonder, what could be a problem if this was much more persistent? So one assumption we have made is that this returns back to steady state before period 500. And we can see that now it returns to steady state rather late, it seems like. So perhaps if we set this up, then at some point we will actually have problems solving the model. Now this continues to be, but now you can see that it has not returned to steady state before, and therefore it makes a bit weird stuff here. So that's a problem. You need to ensure that if you do a shock, it actually does return to steady state before the 500 period. So that's something you need to take aware of. We can of course just increase the truncation horizon, and in this way solve for the more persistent shocks. But with a sort of normal shock here, then it works just fine to have 500 periods. Okay, one thing you can also do in this model, which is that you can think about, we again start from steady state capital, but now we set technology equal to steady state to begin with, but then starting from period capital J, which is period 50, there is a shock similar to the one we had before. And again, we can now solve the model, and we can see, okay, what goes on here. And we can see that actually now what happens is that at period 0, we learn that at period 50, there will be on 50 periods ahead, there will be an increase in technology. So therefore, we don't want to invest a lot now. We rather want to consume and then wait and invest more when we can actually produce much more efficiently, and therefore we end up having sort of this first downward movement in capital, and then an upward sloping path of capital, and then back to steady state again as the shock dies out. Important takeaway here is that we could actually see that households response before. We also do something like this, where then we say, okay, now let's actually I actually don't know why did I want to have it. Let's just forget about this cell here. Okay, so we conclude here that households are forward-looking and responds to this before the shock, and that shows sort of the power of this model in terms of modeling behavior. Okay, so there's many possibilities for how to extend the analysis I just done here. You can add different shocks, for example, like discount factor shocks. You can think of multiple shocks. You can think of permanent shocks where there is a convergence to a new steady state. You can think about how fast is the transition, what determines that. That's easier to evaluate numerically than algebraically. You can also begin to extend the model. You can add a government, a taxation. You could endogenize the labor supply decision. That would mean that now there's sort of further organization for labor supply, and that needs to be sort of a thing that has to be that has to be matched all the time. That could be with increasing equation system to having 3 instead of 2 elements per period. You could begin to add additional assets, housing into the model, add nominal rigidity, so have a new Keynesian perspective, and sort of these are things that are possible based on the code here. In terms of further perspective, sort of if you go beyond this course, then you can think about that there is something called Bewley-Hoggart-Argyle models, which are very similar to what I just did, but where households are heterogeneous and they make decisions under uncertainty and Boring constraints, as in the dynamic optimization lecture. So that sort of that builds upon the Ramsey setup that we have here. You can read more about it on this link here. It also, in this way, if you take a Bewley-Hoggart-Argyle model and you add nominal rigidities to that, then you have what we call a Hank model, a heterogeneous New Keynesian model, which is something that we, for example, teach in advanced macroeconomics, heterogeneous aliens model. There's a link to the course page here. Thank you. That was all for today.